Be our last video on general relativity. And anyway, this is the last thing about this one specifically to black holes. This is, the fun one right here, black holes. And the specific type of black hole that we're really going to be interested in is a Schwarzschild black hole. It's basically a non-rotating, non-charged black hole. And so it's kind of the simplest situation we can look at. So the first thing we need to define is a few things about a black hole. First off, the very center of a black hole, where everything's supposed to thought to go, that's called uh, that's called the singularity. Outside the singularity, you have a sphere that surrounds it. Oops, that's called a sphere that surrounds it. That's called the event horizon. And if it's a non-rotating, non-charged black hole, this event horizon is going to be symmetric. It's going to be spherical all the way around. Let me just fix that a little bit. And this is the point at which nothing can escape it, not even light. So this is the event horizon. Once you go inside there, you're basically doomed to end up in the singularity. There's no escaping. Not even light has enough energy or speed to get out of this event horizon. And then there's actually something that's a little less well known. Outside this event horizon, there's another sphere further out from it, and it's called the photon sphere or the photosphere. It's called we'll call it the photon sphere. And here, this little right here, this distance out is actually the distance out where light could be put in orbit around the black hole. So a photon that would come in, perpendicular to the surface of this way could actually get caught and go into orbit at this distance. That also means that anything inside the photon sphere, any light inside the photon sphere won't escape unless it is pointed exactly perfectly out radially. So inside the event horizon, no light can escape no matter how it's pointed. Inside the photosphere, the only light that can escape is light that's pointed out directly radially. That little bit here, this photon sphere part, usually is just a little extra, not something you really need to know for this course, but it's pretty interesting anyway. You can have light in orbit around a black hole, and inside there, any light that's not perfectly pointed straight out away from the singularity is doomed to not escape as well, but light that is pointed perfectly straight out inside the photon sphere can still escape. So that's just a few things about what we're talking about for a black hole. The singularity is this point. There's a lot of debate about what goes on there. Basically, depending on what coordinate systems you pick, Einstein's equation, they basically blow up to infinity there. Lots of bad stuff happens there. That's where we have no idea what happens at the singularity. It's the point where all our physics breaks down, basically, and it doesn't work. Okay, so what we're interested in is doing something along what is called the Schwarzschild metric. I mentioned it in the last video. Schwartz, man, I always mess this up. Schwarzschild. I'm not sure I spelled that right. Schwarzschild metric. I feel like there's something like SWCH, Schwarzschild. But anyway, it's Schwarzschild metric, and it looks like this. D tau, this is going to be a little confusing for you, d tau squared equals, and then right here you have a 1 minus 2mg over rc squared, okay, times dt squared, and then minus, what you'll have is a 1 minus 2mg over rc squared again, but this one's to the negative 1, and this is dr squared, where dr, basically it's this times dx squared, this times dy squared, this times dz squared. So this is like that metric that I talked about with the signature for special relativity. Time is positive, the spatial dimensions are negative, so minus, 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 so it's a plus, minus, minus, minus. You can write a version of this where it's minus, plus, minus, plus, plus, plus. in which case this stops being d tau and is dr squared. This is what is called proper time. This would be like the dilated times and spaces and stuff like that. But this is basically the Schwarzschild metric for a non-rotating, non-charged black hole. The simplest little version we can get that solves that big crazy thing of Einstein's equation. But this is the metric for it. Okay, and this metric gives us a couple of very interesting things. And if we look at this right here, just this part here, if you notice that 2mg over r c squared, just looking at that term right there, 1 minus 2mg over r c squared. Well, what happens at first is this c squared's real big, but what happens when if 2mg is smaller than rc squared, then this number is less than 1 and we get 1 minus a number less than it. But if 2mg reaches the value, 2mg equals the value of rc squared, then this is 1 minus 1, it becomes 0. And then if 2mg gets any bigger, then this becomes 2mg, a bigger number over a smaller number, and the sign of this flips. And remember, this metric is set up so that time has a positive signature and the spatials have negatives. Well, if this flips sign, then this is in front of time, then the time dimensions become negative and the space dimensions become positive. And it turns out we're going to define the position where that happens as, you guessed it, the event horizon. All right, because that's basically where that actually ends up occurring. This is at the event horizon. When 2mg equals rc squared, what we're going to do is call that r, we're going to call it the Schwarzschild radius, rc squared, 2mg. And then if we solve for the Schwarzschild radius, it is 2mg over c squared. And this is essentially the radius of a black hole out to its event horizon, where once you're inside there, you're doomed to end up in the singularity. You can't get away from it. But the interesting thing about this, looking at it this way, is once you pass inside that event horizon, time becomes space-like and space becomes time-like. That means this singularity that's supposed to be a point in space when you're looking at it from the outside becomes a point in time. And so it's like a point in time in the future, and it's impossible to avoid the future. Time keeps moving forward, and you'll end up inside the singularity. But you may have watched some videos on this or something, and they've talked about how once you go inside the event horizon of a black hole, that time and space, their roles change inside a black hole, and all these weird things happen. But this is what they're talking about. This would become negative, and this would become positive because it's minus and its sign would flip too, and it becomes positive, and they switch. So space becomes time-like and time becomes space-like inside a black hole, and that's what people are talking about. And so let's kind of diagram this out. So remember, our equivalence principle says that we can replace any gravitational field with an acceleration in flat space. So what that means is we can actually go back to our Minkowski space, right, to these Minkowski diagrams. And we're going to do that, and we're going to put our light cone in here, right, 45 degrees both ways, 45 degrees. This is our light cone, and once you're inside a light cone, you cannot get outside of a light cone. Well, to me, under an acceleration type situation, that sure sounds like the event horizon of a black hole. So this is position, this is CT up here. That sure sounds like a black hole. So a light cone in flat space uh, basically is equivalent to an event horizon. So this light cone, this is our event horizon, right? So we're replacing the physical black hole being there with some sort of acceleration we're going to look at here. So event horizon. Now, how do you represent someone who's just sitting out here, like in their rocket, right? They're in their rocket. They have their boosters firing, keep them, and they're just hovering above a black hole, not falling into it, just sitting still. Well, if they're sitting there, they're going to experience gravity, right? They're going to be stuck on the floor of that spaceship, and it's going to be gravity for them. Well, how would that look like here? How do you do that? Well, how do you create gravity inside your rocket ship? You accelerate. So you would be starting with a very low velocity, right? A very small velocity, and then you would speed up. And as you speed up, remember on these, the more horizontal your line gets, the faster you're going. And so you would speed up and you'd speed up and you would just keep speeding up. This is an acceleration. It's a curve in this Minkowski space, and it would be hyperbolic. It would come closer and closer to this light cone or event horizon, if for the equivalence of a black hole. Uh, it would be closer and closer to that, but never quite approaching it. So this could be you just hovering above it. Hovering above the black hole is equivalent to accelerating like this in space, never able to actually, quite cross it. And so uh, remember, what we're doing here is making, down here, we're making an acceleration situation that has all the same properties of a black hole, because that's what the idea is. You can always come up with an acceleration situation that perfectly mimics a gravitational situation. Now, we said the singularity here was a point in time, and it has to be inside the black hole. Well, this is inside the black hole, and the singularity becomes time-like. It has to be a point in time. Points in times are hyperbolas. So somewhere up here, we're going to have some hyperbola that's a point in time, and it's our event horizon, right? And it gets over here, and it gets closer and closer, right? That's what these hyperbola do. They asymptote to our light cone, right? If we continue our light cone out further, right, the light cone comes out like this, and this is going to approach it, and this is going to come over and get closer and closer to it. But this is our singularity. It's a point in time. After we cross that, we have no idea what happened. So let's say this is us, and we're on the spaceship, and so it's equivalent here. This is us, the spaceship. We're going to call A. So this is the movement of A, and then what we're going to do is we're going to have someone here who's going to jump out, and they're going to fall into the black hole. We'll call it person B, right? So astronaut B jumped out and went into the black hole. Well, what would that look like on here? Well, we're here, and person B is just going to leave. He's going to fall into the black hole, right? So this is person B falling into the black hole, right? This is them. They're falling in. This is person B. So what's it going to look like for everybody's perspective? Well, remember, light only moves in right angles. So as we're watching this guy, we'll do his light in blue. He's going to send out a flashlight bulb to us every unit of time, every time his clock ticks. First one's going to come at 45 degrees. We're going to get it here. The second one he's going to send out is going to come along, and it's going to take it a little longer to get to us. So he looks like he's slowing down a little bit to us, because up here, again, we're stationary. We don't notice anything. We think he's the one falling in. We think we're stationary. And then he's going to send us another signal, and it's going to take even longer to get out to us. And then it's going to take even longer to get out to us. And so as he gets closer and closer to the black hole, his signals that he's sending out are getting harder and harder to reach, because remember, this is our thing. We're approaching that light cone, but never getting to it. We're staying outside of this. That's equivalent to this. And his signals take longer and longer to reach us. So if we're watching him fall into this black hole, we see him moving slower and slower and slower. And his time starts slowing down. But once he crosses this event horizon, if he sends out a beam of light now, we'll never get it, because we never cross into that event horizon. The only way we could get it is if we turned off our boosters, stopped accelerating, and allowed ourselves to fall across this event horizon, which we could do, but we're assuming we're not. We're going to hover here forever and never go in. Well, then we're never going to see this signal here. This signal he sent out, it's never going to get outside that light cone. We're never going to be able to see it, and eventually that signal's even going to come up here and hit the singularity. And no matter what he does, he's B, he's in here, no matter how he tries to move, oops, I changed colors. No matter how he tries to move, no matter how. Okay, so sorry, I had a little break in there, but hopefully I got this lined up pretty well enough. But anyway, as we were just saying, once B crosses the event horizon, then A can never see him again. But on his way in, this light would just get kind of crunched closer and closer, and he'd be slowing down. And in fact, A would never even see him cross the event horizon. He would just appear to fall down, and this last beam of light that he would send out right before crossing the event horizon could never actually be quite reaching A, because it'd be like right on the border. So A would just, you see it get slower and slower and slower and slower as he approached that event horizon. What And then once B got inside here, of course, he's doomed. No matter how he tries to go, he can't go faster than a 45-degree angle. He can't get back out of this event horizon, so he's doomed to eventually hit that singularity no matter what he does. It's an unavoidable point in time. Uh, but then what does B see as he's falling in? Well, let's do A's light. A sends out light here, 45-degree angle. Right, he sends it there. There, B sees this. And then A sends out another light signal. A sends out another light signal. The only thing, even after he crosses this event horizon, the light can still go in there. And what does B see? Well, nothing. He just sees A getting further and further away from him. That's all he sees is if he just, let's pretend he kept going straight, these beams of light would keep coming in. B would keep going straight, and he just sees A getting further and further away from him. Of course, eventually hits the event horizon. That's pretty much it for him. But crossing this event horizon, very uneventful for B. I mean, in reality, it's very uneventful for each individual particle of B, but the particles would probably be ripped apart uh, as it crossed over this event horizon. But the idea is for each, if person B was just the size of a particle, he wouldn't even notice crossing over. For him, there's no difference, and he would just watch A basically fly away. So as B would fall into here, he'd look up and he'd see A just getting further and further away and shrinking further off into the distance as though he was falling away. And if you watch the movie Interstellar, you actually see that happen when he falls into that black hole. Hope I didn't ruin it for anybody, but he looks out and he sees the whole universe just kind of recede away from him real fast and get smaller, as though it was accelerating away from him. That's what he would see. And so that's basically what would happen, and that would be the view point of both these, because this whole accelerating frame we've set up here has all the exact same properties as this black hole here, and therefore should be the same. Now the last little thing about that space-like to time-like, along here, when you're out here, it's all time-like, but once you cross inside here, it's basically like they switch positions. So you would move along, and then you start moving through time. Right? Time becomes like the space-like thing. Now, whether or not there's something funky that happens when you enter inside the black hole and time really does become like a space you can move around or not, I don't know, or if it's just a mathematical artifact of this or something. I'm not 100% sure nobody's ever fallen into one, but there it is mathematically. There is some sort of switching that occurs there. Okay, that should be pretty much it for the idea of black holes that I wanted to go over. And make sure you know this Schwarzschild radius here. You could even calculate this for Earth if you wanted. Put in the mass of Earth, put in G, put in C squared, and find how if we crushed all of Earth down into a black hole, what would its event horizon radius be? Its Schwarzschild radius be? If memory serves me, it's only like a centimeter or something like that in size. It'd be very, very small. Okay, that's I think it.